Stripping down science. The Naked Scientists.
Why do we see stars when we take a knock on the head? How does a fly fly in a rising or dropping lift? And do slugs and snails feel pain when you dose them with slug pellets? Hello, it's Sunday, June the 17th. My name's Chris Smith, and also with us today for our Naked Scientist Science Phone-In Extravaganza is Diana O'Carroll. Hello, Diana.
Hello, and also on the way, news this week from outside the solar system. The Voyager probe is now picking up powerful radiation signals in deep space. But what does that tell us? Plus, I'll be heading to the kitchen with Dave Ansell. What have you got in store for us, Dave?
Well, I'll show you how to make some amazing slow-motion waves inside a bottle. If you want to have a go, you'll need a bottle, a couple of litres of cooking oil, and if you want to make it look pretty, some food colouring.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And Karen got in touch with us, and she's been doing, I guess, a bit of gardening. Hello, Karen.
Hello, Chris. How are
what have you been doing in your garden?
Well, at the moment, I'm a cut flower farmer's apprentice, and we grow lots of seedlings and young plants, but they've suffered a lot with slug and snail damage this year, and we don't like killing them, so we've been trying various methods of management, but wondered if they actually do feel pain and what's the most humane way to deal with them.
Someone actually asked us a little while back whether fly spray is painful as a way to bring blue bottles to their end. And when I said, well, it probably wasn't very pleasant for the fly, they said, oh, good, well, I'll use it more then. I wasn't actually sure about the answer to this to start with, whether things like slugs and snails do actually feel pain. I mean, the way that the medicines and the drugs work that you put into slug pellets is it basically just causes them to expire through various toxic ways, which are not are going to affect humans and other animals and mammals. So basically you're exploiting a chemical problem that the snail has when it eats this stuff compared with us. So they're pretty safe. But I went to have a look at a story I wrote about 5 years ago, Can Prawns Feel Pain? Because Bob Elwood, who's at Queen's University Belfast, published a paper showing that prawns, when he dabbed vinegar onto their pincers and on their antennae, seemed to flinch. And he suggested this was because they felt pain. Then I found that he's actually published a follow-up paper, and I've looked that up for you, and it says here, I'm actually quoting from Science Daily, but it says here, new research published by Queen's University Belfast academic has shown that crabs don't just suffer pain, but they also remember it too. The study looked at the reactions of hermit crabs to small electric shocks, and it was carried out by Professor Bob Elwood at the School of Biological Sciences at Queen's University Belfast and published in Animal Behaviour. Professor Elwood, who's previously carried out a study showing that prawns endure pain, said that his research highlighted the need to investigate how crustaceans used in food industries are treated. Now, obviously, this is about crabs, and you're asking about slugs and snails, but they are very closely related in the grand scheme of things, and therefore it's reasonable that if we read what happens to a crab, we can sort of extrapolate to a snail. Now, he goes on to say, wires were attached to the shells of the hermit crabs to deliver small shocks to the abdomens of some of the crabs in the shells. The crabs that got out of their shells were those that had received shocks, indicating the experience was unpleasant for them, and it shows that central neuronal processing, in other words, they realised it was unpleasant and they decided to vacate their shell. It wasn't just a reflex response. He also says that crabs that had been shocked but had remained in their shell appeared to remember the experience of the shock because they quickly moved towards a new shell when they were offered one compared with the shell they were already in. In other words, they prefer certain shells over others, and if they're in one that they're already a bit uncomfortable with and you then shock them, they're much more likely to vacate the premises and go for a new shell. So this would suggest that simple creatures like prawns and also crabs and hermit crabs can experience pain. Therefore, I think it's probably not unlikely that if you bring a snail to an untimely end by pouring salt all over it or poison it with some slug pellets, it's probably not very pleasant for the slug or the snail.
Wow, okay.
So maybe we can ask our listenership whether they have any recommendations for getting rid of or deterring slugs and snails in a way that won't necessarily make them feel pain. Maybe the Guinness trick would work because they'll be so drunk they wouldn't notice.
Yeah, that would be really interesting, actually, to hear what other people have got to say.
Or maybe they will ring us up and tell us. Thank you very much for your question, Karen. Now, Diana, I have a question here from Dr. Nicola, who says, I have two related questions. It has been suggested that the Vikings extracted cod liver oil by fermenting liver. The raw livers were emptied into open vessels and left there. When the weather grew warmer, the cod liver oil separated from the livers and floated up to the top and was skimmed off. So my question is it really possible to ferment liver? And she also says, I'm aware that in certain cultures, for example in the Sudanese, they produce a dish called miris that's supposedly fermented fat. Sounds ghastly. What can you tell us about this?
It does sound a bit interesting, doesn't it? But all over the world, cultures will ferment various different foodstuffs in order to make them taste a bit more interesting. So the actual process of fermenting usually involves some kind of living organism, like a yeast or a bacterium, and it also involves an anaerobic environment, so no oxygen. And I couldn't find very much information about this Viking method of making cod liver oil, but it does seem that they just dumped a load of cod livers into a barrel, left it in some seawater, and then just sort of left it outside. And presumably what would happen is that you would have bacteria that would break down the liver, and because oil isn't quite so easily broken down, especially this is a serious problem that the sea actually has, the oil would float to the top and it wouldn't be broken down as quickly as the other parts of the liver. And when it comes to fat and Inuit wrapping up bits of fat in sealskin, what was probably happening there is that you have certain types of bacteria, probably bacillus bacteria, which will break down bits of the fat, make it decompose and make it taste quite different. Interestingly, I think about a year ago, just after Christmas, Yorkshire Water actually released a load of bacillus bacteria into the sewers, because one of the major problems that we have in Victorian sewers in this country is that people pour a lot of fat down the sink and it builds up into great big lumps and blocks up the sewers. So what the water company did was they flushed a load of bacteria down there to break it all down.
And not already lots of bacteria in the sewer?
Obviously not the right kind.
Wonderful story, that. Thank you very much, Diana. If you have any questions for us, email chris@thenakedscientist.com. You can even send in a recording of your question by email and send that over to us, which is what Gabrielle did.
Hi Naked Scientists, my name is Gabrielle Kelly and my dad has a question that he was wondering if you could answer please. He recently bought some rechargeable batteries for some of our toys, and as he was doing the first charge we wondered about the efficiency of recharging batteries. Is it an efficient process regarding the amount of power or energy going into the battery as compared to the amount of power that is stored and used? Cheers from the land of Oz, we love the show. Thank you.
That all rather depends on what you call an efficient process. Certainly not all of the energy which you use to charge a battery will come out of the battery in the end. So you can feel that by just feeling the battery while it's being charged. It gets warm, so that must be energy being wasted. If you look at the efficiency of charging sort of a standard sort of nickel cadmium or nickel metal hydride battery, the efficiency is sort of 60-70%. So you're sort of wasting 30 or 40% of the energy you're putting into the battery itself. And you're probably also wasting some more energy in the charger, because that's not going to be 100% efficient either. So you might be talking about half the energy you're using is actually ending up in that battery. So that doesn't sound very good. But if you're going to use something with a battery, you need some power and you need to get it from somewhere. And if you compare that to using a throwaway battery or something, that's going to be, I would have thought, only a few percent efficient, 1 or 2% efficient, because you've got to get the materials to make the battery, you've got to refine them, you've got to then put them all into a case. And so it doesn't sound very good, but it's far, far better than any of the alternatives.
Dave, thank you very much. Diana, this one has come in, a disgusting question. You've got to hear this.
Hi, this is Lisa from Las Cruces, New Mexico, and I was wondering if there's an evolutionary reason for why humans find cockroaches so repellent. I know we associate them with dirt and decay, but they're not poisonous, and some cultures eat them, but overall they seem to gross people out. Why is that?
Well, it seems to be an almost entirely cultural thing. There was a study done last year by a group at the Karolinska Institute in Sweden, and they looked at toddlers and small children and sort of introduced them to various creepy crawlies and snakes and things, or showed them images of them, and found that actually they weren't scared of them. There was no sort of flinch effect like with the prawns, and there was no expression of fear. But what they did find was that the children learned to fear things much faster than they learned to sort of understand things that weren't things that they should be afraid of. So when they showed an image of, say, a snake or a cockroach and played someone's voice, which had a sort of warning tone in it, the children learn much faster that they should be afraid of this. And so this is probably what's happening when people learn to be afraid of spiders. There's probably a parent around going, "Oh, it's a spider," and that's how they pick it up.
How do they go again?
It's a spider!
I remember watching a doco on the telly, and it was a psychologist in America, and he was demonstrating what you've just discussed by giving children bedpans to drink drinks out of. And they were quite happy to pour apple juice, which obviously looks a bit like urine, out of a bedpan and drink it until they knew it was a bedpan. But the interesting thing was when he put a cockroach in the bedpan with the liquid, they then wouldn't drink it because they said it had a bug in it.
Oh, that's interesting. How old were they?
Well, he said there was a threshold
enough.
age, and once they got to a certain age, they then started to recognise that this isn't quite as seemly as it should be, and so they said, "No, I won't drink that because it's got wee in it," and things like that. They sort of have this aversion to bodily function, which sort of kicks in from about age 4 or so. Whereas before that, very young kids quite happy to play in their own poo, aren't they?
I wouldn't know about that. Maybe you, Chris, not me.
I've got 2 of them, I should know. You're listening to The Naked Scientists, Chris, Dave and Diana. Heather Williams has got in touch and sent us a tweet at Naked Scientists and says, "Why do bits of kids grow at different rates? Legs lengthen, then arms, one foot gets bigger than the other. Can you shed some light on this with your sort of paleoanthropology hat on, please, Diana?"
OK, well, I think genetics is probably a major determinant. Certainly I was disappointed when I didn't grow quite as tall as my sister, who has a different father who's obviously taller. Oh, I'm so disappointed. But also there's a nutritional element to it. So if you've got lots of protein and good vitamins and all that stuff in your diet, then you're going to grow a bit taller. Disease actually can affect how tall you end up as an adult, especially if you have some major disease during your childhood. So one of the things that we find in archaeology is that when people started farming and living in very built-up environments next to each other, they got more diseases and their heights actually reduced, whereas the hunter-gatherers wandering around a few thousand years before were quite a bit taller and healthier. And also there's gender as well, unfortunately. Girls generally don't tend to get as tall as men, sadly.
So there's a combination of availability of food and the interaction of your environment with your genes, but also genes control your body at the level of individual tissues develop at different rates as well, don't they? So it makes sense. Your body puts itself together in the right order so that you're growing at the right rate to support the right size frame. So your liver and heart don't turn into an adult liver and heart, for instance, in a very young baby. Everything grows at the right rate, and that at the end of the day is going to be programmed by genes too, isn't it?
Yeah, and there's also the question of when your bones fuse as well, because that's one of the things that the archaeologists look at as well. The collarbone is actually the very last bone to sort of fuse, and that's when you're 25, and presumably you should have finished growing, but actually your bones haven't finished growing technically.
Ain't life a funny thing? Thanks, Diana. Neil's on the line. Hello, Neil.
Hello, Chris.
Fire away.
The other day I picked up the remote control that controls my hi-fi and found it was hot. And not only that, it wouldn't work. The batteries had obviously died, but there's clearly energy in there. So I'm wondering what chemical reaction is going on in there that causes it to overheat but stop producing enough energy to let the remote do its job.
Dave.
Okay, as I was talking about earlier, charging batteries isn't 100% efficient, and similarly discharging batteries isn't 100% efficient. The way electronic engineers like to think about it is that the battery has a resistance, so if you draw a current from that battery, you're pushing that current through a certain resistance, and so it will heat up. So if you short out a battery, so if you basically take a wire from one end of the battery and connect to the other end of the battery, then you will cause, there's no resistance anywhere else, there's nowhere else for the energy to go, so all that energy will get dumped into the internal resistance of the battery and it will get very, very warm. And so, one thing which could have caused it is that your remote control somehow shorted itself out. That could have been both in the remote control itself, but if you change the battery and it worked fine, then probably not. But it could also have been inside the battery. Something could have gone wrong and some wires, some bits of metal touched inside the battery.
I was going to say, it sounds like if nothing else is to blame, probably the battery has developed an internal short and shorted itself out, and it's dissipating all the energy into itself, making itself get hot.
Yeah, certainly in a remote control, because the remote controls draw so little current that there shouldn't be enough power being dissipated anywhere else.
Coming up, Dave's going to show you how to make some really quite funky waves in slow motion in front of your very eyes in your kitchen. You just need a lemonade bottle, you'll need some cooking oil, about 2 litres of that, some water, and if you want to make it look pretty as well as look pretty fantastic from a physics point of view, then you'll also need some sexy coloured food colouring. I'll leave the colour choice entirely up to you. That's coming up. First, though, homegrown vessel replacements. The first replacement tissue-engineered vein grown from a patient's own stem cells has been successfully transplanted into a 10-year-old Swedish girl. This has been written up in the journal The Lancet this week. It's by Michael Olausson, who's a researcher at the University of Gothenburg in Sweden. And what he and his colleagues have done is to treat a 10-year-old girl who had a problem called portal obstruction. And the portal vein is a very large blood vessel that drains blood out of your intestines, takes it to the liver to be processed in the liver before the liver then releases the blood back into the rest of the circulation. And if you obstruct that vein, then what happens is that the blood can't get back out of the intestines properly, so it finds other ways around the obstruction, and this can cause other blood vessels, including those in the esophagus, to become dangerously dilated, and if they do that, then they can hemorrhage and bleed. It also causes the spleen to become too large. Normally what you would do is to try to find a way to replace the obstructed vessel. And one way to do that is to borrow a vein from somewhere else. In some cases they borrow a vein from the leg, including the long saphenous vein. In other cases they go to the neck and they borrow the jugular vein. You can imagine the trauma of doing this sort of surgery. You don't really want that, especially in a 10-year-old girl. So what they did was to go to a person who had unfortunately died, cadaveric donor. They took a section of the iliac vein, which is the large vein at the top of the leg, where it goes back into the two veins from the legs unite. They put that vein section into detergent solution, and this destroys all of the cells from the donor, and it leaves behind just a scaffolding of the connective tissue that used to hold those cells in place. They then got stem cells from the girl's bone marrow, added them to this scaffolding, and put the whole thing in what they call a bioreactor. Effectively, it's a dish kept at the right temperature with some nutrient solution and growth factors. And after a month, the stem cells had grown into the right place in the blood vessel to turn into muscle cells and had completely replaced all of the muscle that you would normally find in the middle layer of the vessel. And then they took some endothelial cells, which are the smooth cells that line blood vessels, and added those, and they coated the interior. That produced an appropriate section of vessel, and that was then taken out of the culture dish and transplanted into the girl, bypassing the injured or damaged bit of her portal vein, and she made a full recovery. They had to go back in and extend the bypass later because unfortunately the graft developed a bit of a kink, but she's now much better and at school and doing very well. And as they say in their paper, the new stem cell derived graft resulted not only in good blood flow rates but normal laboratory test values and a strikingly improved quality of life for the patient. Quite striking, isn't it?
How do the cells know that they should be kind of growing on the scaffold and not sort of on the rest of the Petri dish?
The cells have what they call adhesion molecules on their surface, and this is like cell Velcro. So cells have sticky molecules on the surface, and the scaffolding has the right thing that docks with those sticky molecules. And probably the cells know when they've bound onto those things, so they know they've locked onto the right environment, and that in turn tells the cells what to turn into and how to behave. So one thing controls the other. And the benefit of doing it like this is that then the cells are entirely the girl's own. They're not donor cells, so there's no risk of immunosuppression being needed because there's no risk of rejection or anything like that.
How big a step would it be to do this with arteries then? Because people, especially in old age, will have a lot of problems with arteries, so how could this help them?
You're absolutely right, and 1 person in 3 develops some kind of vascular disease that will kill them. I was going to say in their lifetime, but that would be a rather fatuous thing to say, wouldn't it? But it's a major problem, and the problem with arteries is they're much higher pressure, so they have to withstand a much greater tension in the wall, but people are very close, and they've actually got arteries that can be produced artificially. This was a first because it's the first time anyone's done it with a vein, but they are now quite close to producing arteries as well. The problem is getting to people who have these diseases before they actually develop the problems in the first place. But good question. Thank you, Diana. Now, if you'd like to ask a question here on The Naked Scientist, remember it's Chris Smith, Dave Ansell and Diana O'Carroll. We're answering all of your science questions. Just email chris@thenakedscientist.com or tweet @nakedscientist.
Distilling the best science. The Naked Scientists.
Right, Dave. Blaine has got in touch by email, chris@thenakedscientist.com. He's in the US, and he says, why is it that a fly caught in an elevator, and he helpfully translates that lift for us here in England, doesn't hit the floor when the lift goes up, or conversely hit the ceiling if the lift goes down? What do you think?
You've got to think about the forces on a fly. It's got two big forces on it. There are gravity pulling it down, and then there's aerodynamic forces pulling it up. If you effectively let the lift start dropping, then effectively gravity is reduced because the lift is accelerating downwards, so there's less force upwards on the floor on everybody. And essentially the lift is moving down around the fly. Now, to start with, the fly has got quite a lot of inertia and it's just going to sit there, essentially stay still, and the lift is going to move around it. But a fly has got all sorts of complicated algorithms going on in its head to try and keep it where it wants to be. And I would have thought what goes on is essentially that the fly notices that it's higher than it wants to be, so it stops flapping its wings as hard, so it will tend to drop down within the lift. And so it stays where it wants to be, essentially just because it flies to where it wants to be.
So if the fly weren't compensating, which is your answer, it probably would go visibly upwards or downwards according to which direction the lift was moving in.
Yeah, and probably if the lift suddenly jolted downwards, then the fly would stay still and the lift would move around it, and it would move upwards.
Thank you, Dave. John's on the line. Hello, John.
Hello there.
What can we do for yourself?
Well, I'm embarrassed to ask this question, but first of all, let me start by saying your show is the best thing ever happened to the radio. I haven't missed a single broadcast since you started. My question is, why do we see stars when we bash our head? I've been studying the eyeball for 30 years, and I haven't got a clue. What makes it more confusing is that I also, and I think most people do, sometimes see stars of the same sort when they stand up suddenly and their blood pressure drops briefly. So I'd really love to know the answer to that question after all these years.
John, I think both of them are basically artificial phenomena in the sense that in one case, the standing up too quickly, this is an entoptic phenomenon, something going on inside the eyeball. The retina, as you'll know as an ophthalmologist, as you say you are, has one of the highest metabolic rates of any tissue in the body. The brain and the central nervous system tissue burns off about 20% of the energy that you consume in any given moment in time, and it contributes only a fraction of body mass, so it's very metabolically hungry. And if you stand up too quickly, then you have what's called postural drop. Your blood that's coming up from your legs into your heart to then get pumped around the body, the perfusion pressure drops just briefly when you're standing up and before your heart compensates. And that causes there to be a momentary reduction in perfusion to your retina, and that slightly reduces the supply of oxygen and sugar to the retina from the blood, and that causes the retina to start to fire off abnormal signals. Because when you deprive the retina of the right blood flow, then it starts to fire off these abnormal sparkly light signals, fooling the brain into thinking you're seeing light when it's not there. Now, conversely, when you bash your head, what's probably going on there is that because the brain is bobbing around inside your head in a fluid, the cerebrospinal fluid, and has a very wishy-washy consistency, a bit like blancmange, really. If you have a sudden interruption of movement to your head, so you hit your head very hard against a wall or a pavement, the brain then cannons inside the head into the front of your skull and then can rebound and hit the back of your skull as well. And if you irritate the part of the brain that decodes what you're seeing, the visual cortex, which is right at the back of your head, then it's possible that in the same way that irritating the nerve cells in the retina by not having enough blood flow makes you see funny stars, it's possible that you can also affect the brain cells directly at the back of the head, and I think probably that is responsible for triggering these funny stars that you see when you suffer a head injury. But it's an excellent question, and thank you very much for asking it. Now, this one, I think this is a bit specialist. David White has been down a mine. He's got a question for you, Dave.
Hello, Naked Scientists. I thought up this question while sitting a few hundred feet underground in a slate mine in between taking photos. I know weakly interacting neutrinos can be detected a few hundred feet underground in mines. My question is, if I'm sitting underground in a mine without any lights on, how long would it take for a neutrino to strike my retina, and would the product of this strike be visible? Is it more likely that that had happened to my photographic sensor? And the same question applies.
Okay, this is very interesting particles, neutrinos. They are almost don't interact with the rest of the universe at all. In fact, the neutrinos, which are coming from the sun, billions and billions of them are being created in nuclear reactions in the sun. And they can travel the equivalent of 10 times the distance between the Earth and the sun through water before they hit anything and make any kind of interaction at all. And not all of those interactions will actually produce a light which you'll be able to see. So just working on the number of interactions. So that sounds incredibly unlikely, but there's also about 65 billion neutrinos going through every square centimetre of everything in the world all the time, every second. And if you work out the relative ratios between the distance, how often they interact, it's probably in a cubic centimetre, so your eye is very roughly about a cubic centimetre. In that liquid in your eye, it's probably going to take about 200 seconds for a neutrino to interact with some of that liquid. Now, how many of those produce enough light for your eye sensor to see is probably going to be a relatively low proportion. So you're probably talking thousands of seconds. Every few hours, maybe a neutrino hits your eye and produces some light. But actually, for you to be able to see that, I think that's almost entirely unlikely because it's going to produce a tiny amount of light. And the sensors in your back of your eye are getting triggered by thermal radiation, probably just radiation from radioactive elements inside your eye and in the atmosphere around the place is going to be far, far greater effect than neutrinos. And I think the camera sensor is probably even less likely for this to happen because the camera, your eye is full of water, which will interact with neutrinos, whereas the camera sensor in front of it is full of air. Therefore, there's less particles for the neutrinos to interact with, and therefore you're basically only talking about interaction with the very thin layer of your camera sensor. So probably slightly more likely with your eye.
Dave, thank you very much. You're listening to The Naked Scientists, Chris Smith, Dave Ansell and Diana O'Carroll. It's exam time, and across the country there are tens of thousands of young people who are sitting public exams that will determine their future, including whether or not they go to university. But Michael Gove, the Secretary of State for Education, wrote recently to the examinations regulator saying, and this is in his letter, "I am increasingly concerned that current A-levels, though they have much to commend them, fall short of commanding the level of confidence that we would want to see. Leading university academics tell me that A-levels do not prepare students well enough for the demands of an undergraduate degree, and I am troubled by reports from learned bodies such as the Institute of Physics." As a result, the government want the exam boards who develop A-level exams to fundamentally change the way that they operate. And joining us to explain what this might mean is Colin Black. He's from the Cambridge-based exam board OCR. They set about 25% of the papers that are sat by learners in England. Colin, welcome to The Naked Scientists.
Thanks, Chris.
First of all, what does the government actually want you to do differently?
The major change the government is looking for is for us to work, when we're developing the A-levels, actually with people who work at universities. So rather than sort of us developing them with our experts, third-party experts that we would sort of talk with, and also the various sort of professional organisations, they've asked us to open the door and actually start speaking to people in higher education.
What do you think has provoked Michael Gove to say, and I'll quote again, A-levels fall short of commanding the level of confidence we want to see, and university academics are telling us that A-levels do not prepare students well enough for the demands of their undergraduate degrees?
Well, I don't think that statement's really come as a surprise to us. Ourselves and also our sort of parent organisation, Cambridge Assessment, have been undertaking some research over the last sort of 18 months or so. We've been talking with people from HE, we've been talking with professional organisations. There's a general sense that there's just that sort of gap between the A-level student as they enter higher education and some of the skills that are required isn't necessarily sort of about the full sort of content of the subject areas, but maybe a bit more about sort of being able to explain things in more depth, things around sort of experimentation, so not just sort of taking the facts as is, the ability for critical thinking, those sorts of areas. And that's what we've been getting back from higher education. So it comes as no surprise that sort of Michael Gove has sort of taken all this on board and sort of come out with the statements that he has recently.
Is this a problem confined just to science, or is this more comprehensive than that? Because I can see it being more of a problem for science because science is moving a lot more rapidly than, say, history is.
Yeah, I mean, you could see difficulties in a syllabus which sort of lasts 5 years and sort of keeping up with some of the sort of new changes and the various knowledge that comes into the body of science. But to be honest with you, I think some of this is around the way that the A-levels have been assessed. So therefore, you could sort of apply some of the problems across the whole of the A-level syllabus.
So what are boards like yours, OCR, doing about this? How are you responding to this call to action, and what are you going to try and do?
Well, as I previously mentioned, we've already sort of set up sort of really strong links with higher education. OCR, of course, is part of the University of Cambridge. So what we'll be looking to do is across all the subject areas, we'll be setting up forums and we'll be setting up discussion groups to see exactly what we want coming out of A-levels. From there, we will set up sort of development panels which we will use and which will include university lecturers, which we will use to actually start developing not just the content but also the way that we might look to assess going forwards.
So the whole emphasis being on more giving people the big picture of their subject rather than looking at it in bite-sized chunks, because I think a major criticism that's often raised to me by students I talk with is that they're being taught in bite-sized chunks. You learn this module of the subject and you learn it really very well and you work very hard and get a good mark in it, but then you forget that and move on to the next module, and at no time does anyone really expect you to link up all of those different little bits of intensive learning to see this big picture that's so important in science.
Yeah, I think you're right there, actually. The way sort of things are going now, we're moving away from modularisation, which is the bite-sized chunk sort of way of learning, to what's called linearisation at GCSE, and I think that'll be exactly the same at A-level. And as you say, it's about linking all these sort of things together rather than being an expert over a short period of time just on one specific area. Now,
when you and I first met, Colin, and we're declaring interest here because you approached me a couple of years ago and asked me to come and speak at an inset day that you were running for teachers. And now I sat down at the lunchtime recess with a lot of teachers and I asked them what they felt the biggest impediment to teaching hard science subjects was. And they were saying to me that actually, for the most part, the last time for many of them they were in a university environment learning like an academic at university may have been in some cases 20 years ago. And they're trying to turn kids into the right sorts of people who will flourish in that environment, but they felt ill-equipped because it was so long since they'd been in it. I think that's probably a reasonable thing, isn't it? So the whole idea of trying to bring educators at higher level closer to school educators together, I think that's probably really, really fundamental to actually making this get better.
Yeah, I mean, one of the things we can specifically do, and we can start sort of doing now rather than waiting for the sort of full A-level development, is professional development activities that we've been looking to do over the last couple of years, but we're looking to expand on. And that is actually sort of bringing a lot of the new concepts within, say, for example, science, and actually trying to explain that to and go into much more depth with that and put those sorts of events on for teachers, because as you say, with the sort of full-time teaching that they're having to do, sometimes it's difficult for them to keep up with the sort of current knowledge and all the sort of various changes that are sort of going on.
And one of those things is something that you've actually asked us to help you with. You're running an event in London, which is intended, and that you're trying it with physics first, but I presume you're going to try and expand this to other science subjects. So we're trying it with physics first. This is to bring a whole bunch of top-tier scientists together on one day and a whole load of teachers and give the teachers the opportunity to hear what is cutting edge in the science world according to those academics, and then interact with them. And then that will hopefully mean they take that message back to the classroom and they can, I suppose, make their lessons more relevant to what those academics' expectations will be.
Absolutely. We've pulled together a number of experts in their fields. We've looked at various subject areas within the A-level, so we've linked all this together to the A-level specification, and we've pulled in people who are able to talk around cosmology and particle physics, and they'll be talking about their specific areas of expertise throughout the day. There'll be opportunities for the A-level teachers, those delivering their qualifications, to interact both with themselves but also with the higher education experts. And as you say, it's about sort of reinvigorating some of the passion some of these teachers had when they first went off to do their first degrees or whatever sort of engaged them with science in the first place, or physics in this particular instance, and trying to get that into them, trying to sort of get that spark that they can then deliver back to the students.
And if people want to come to this, where is it on and when? How do they go about finding out more?
OK, it's running on Thursday the 28th of June, so it's in a couple of weeks' time. We're running it at the Royal College of Pathologists in London. Probably the best sort of thing for people to do if they're interested in attending, go onto our website, www.ocreventbooker, all one word, .org.uk. If they go on there, they'll be able to see all the details and book online.
And hopefully we'll see you on the 28th. And talking of really tough to answer physics questions, we're going to put Dave to the test now. Catherine is with us, and she's got a rather tricky question. Hello, Catherine.
Hello.
So have you got an A-level in physics?
Well, I've got an HND in chemistry. So
you're sort of a scientist.
Quite, yeah.
Where are you based?
Hemel Hempstead in Hertfordshire.
Super. OK, so chemist turned physics. What would you like to physicist? What would you like to ask Dave?
Yeah, it's something you can't answer in 2 minutes, but can you explain to me what the string theory is, and also what proof have we got that these so-called strings actually do exist?
Okay, string theory is essentially trying to explain why we have all the fundamental particles we have. So you get things like, protons and neutrons are made up of even smaller particles called quarks, and you get electrons, and you get sort of higher energy, more exotic particles, things like muons and all sorts of different particles. And they can combine in different ways, and they all have different masses. And people who are much better at maths than I am have spent a long time trying to find mathematical constructs, so ways of putting maths together to produce objects which look like the particles we see and have similar properties which we could call mass. And one of the ways they've done this is with some maths which look a bit like strings. And so you can have oscillations on a string. If you wobble a string slowly, you kind of get one wobble in it, and it wobbles left and right. If you wobble a bit faster, you can kind of get start getting a snake wobble, and they get faster and faster. And these different vibrations could be associated with different particles. The actual strings themselves, probably just maths. We have no evidence to say that there's actual little bits of cotton wobbling very, very rapidly. So all we know is that there is some maths which gives rise to things which look a bit like the particles we have. I'm not even sure that there's any actual evidence to say that string theory is better than any other particular theory. They haven't actually kind of got that far, but that's what the guys in CERN are trying to do.
Well, I hope that has helped you out, Catherine, and thank you very much for the call. You're listening to The Naked Scientists. Chris Smith, Dave Ansell and Diana O'Carroll. We're answering your science questions on The Naked Scientists this week. Now, Dave, we mentioned this at the beginning, this very interesting information flowing back in from Voyager, which is actually nearly the same age as me. It was launched just shortly after I was born, so I sort of feel I'm tied to Voyager, this probe that's heading out of our solar system. Tell us more.
Yes, there were 2 Voyager spacecraft. The first one which was launched was Voyager 1, which is the one we're talking about. It was launched in 1977, and its main mission was in 1979 when it visited Jupiter, and in 1980 when it visited Saturn. But when this main mission was over, it was flying away from the Earth very, very rapidly, and 34 years on, it's still doing science. Now, it's a bit out of date, and its radioactive power source is running down, but it's in a unique position. It's the furthest man-made object away from Earth. It's now 17.8 billion kilometres away from the Sun, which is more than 120 times further than the Earth is from the Sun, and more than 3 times further than Pluto. So by being where no other spacecraft has been before, it can do new science. At the moment, it appears to be right on the edge of the Sun's magnetic field, and it's starting to be overwhelmed by the galactic magnetic field. The solar magnetic field deflects very high-energy cosmic rays created when stars explode, forming supernovae. So as it goes through, there should be fewer solar cosmic ray particles inside this heliosphere than outside it. In the last 3 years, Voyager 1 has seen a 25% increase in galactic cosmic rays. It looks like it's starting to move through. But in May, it saw about a 9% increase, with 5% in the last week of May.
So it's suddenly shot up.
Yeah, that's right. So it looks like it's going through a transition, and that is very, very probably this edge of the heliosphere, and it's about to enter just the empty kind of galactic space. It's got enough power to last until 2025, so hopefully it will get out there and tell us what it's like out there before the poor thing kind of dies of old age.
How does it detect the radiation? What instrument is it using?
It will be using some kind of bolometer, so particles hit it, and then you get an idea of what direction they're coming from and the amount of energy, because the amount it heats up. They call it a cosmic ray telescope.
It's extraordinary that at its great age it is still working and still doing science. I suppose that's a reflection on the engineers as much as anything.
Yes, I mean, really awesome engineering to be able to build something which 35 years later is still limping along and doing science which nothing else can.
Maybe it really is value for money after all.
And now with a roundup of the other science stories hitting the headlines this week, including the plant that detonates a mustard bomb in the mouth of any animal tempted to eat it rather than spit it out. Here's Mira Senthillingham.
Playing music in groups increases empathy levels in young children, according to work published in the journal Psychology of Music. Working with 52 children aged 8 to 11 and exposing them to a range of weekly activities, including musical games or word activities, Tal-Chen Rabinowitz from the University of Cambridge found that children in the musical groups showed significantly increased levels of empathy when tested for compassion and responses to facial expressions. It's thought that the musical activities enabled the children to experience shared intentions and a mutual understanding with their peers.
Empathy is good for everyone, for children, for adults. Empathy has been seen to be a precursor for pro-social behavior. So when we empathize, when we understand the other emotional state, we tend to want to help them. We are we want to look at also children on the autistic spectrum, for example, which empathy might be able to help them in their social interactions. Right now, I think we're concentrating on the regular population.
Electrical signals could be used to monitor cracks in industrial materials and predict their impending failure or breakage, according to work published in the journal PNAS. Troy Shinbrot from Rutgers University in the US used powders such as flour and pharmaceutical drugs to model the composition and movement of materials such as ceramics and concrete, which are made by compressing powders together. The team found spikes in voltage occurring as crack-like defects developed in their models.
Ceramics are used in everything from catalytic converters to artificial teeth. It may be the case that these kinds of products could also exhibit precursors, so one might be able to measure voltages and detect whether or not a failure is imminent in these kinds of systems.
The woolly mammoth had a slow decline to extinction due to a range of factors, including changes in climate, habitat, and living alongside humans. Using radiocarbon dating on samples of tusks, bones, and tissue from the mammoths, Glenn MacDonald from the University of California at Los Angeles found that whilst the animals were abundant 30 to 45,000 years ago in the region of Beringia, which is now Alaska and eastern Siberia, they then migrated, changed in distribution, and fell in number over time due to warming climates, human civilizations, and the growth of forests, with their final extinction about 4,000 years ago.
Despite the fact that they were abundant, despite the fact that they had a widespread geography, despite the fact that they could take advantage of a wide range of climates from the northern coastal regions into the central parts of Siberia, they still, at the end of the day, went extinct about 4,000 years ago. Lots of things we count on for species persistence: rapid ability to recover, the large population size, geographically widespread. We've seen with the mammoth wasn't good enough.
And finally, the tailyweed plant produces toxic compounds in its seeds to aid its spread across the Negev desert in Israel. Denise Deering from the University of Utah monitored the interactions of the plant with predators such as the spiny mouse in both wild and captive environments, and found that when these mice consumed the plant's fruit, they spat out rather than ate the seeds inside. Enzymes within the seeds activate toxic compounds when the seed is chewed, encouraging predators to spit them out and aid the seed's dispersal instead.
So there's this long-standing battle between plants that don't want to have their tissues eaten, but they need to have their seeds dispersed. And this is just a new twist in that battle where this seed predator has now been turned into a seed disperser at the whim of the plant toxins. So it seems, on first glance, that the mouse has overcome the defenses of the plant. But in this game, the plant is actually winning because it's getting the mouse to do its bidding by dispersing its seeds to suitable locations for germination.
And that work was published in the journal Current Biology.
Mira Senthilingam with our Naked Scientist news flash. You can find the transcripts and the references for all of our news this week, and that's on the website at thenakedscientists.com/news.
A major 7-year study has been launched in the UK to investigate the link between biodiversity and the services that nature provides, such as food, clean air, water and flood protection. Planet Earth podcast presenter Richard Hollingham went to meet the leader of the project, David Raffaelli, from the University of York at Black Toft Sands Nature Reserve on the banks of the River Humber in South Yorkshire. The reserve is home to a herd of wild conic ponies, as well as a multitude of bird species. Looking out from a bird hide across the marshes, Dave explained about the benefits of biodiversity.
If you look out at the area we're looking at the moment, you can see it's dominated mostly by reeds. These have many, many functions in the natural environment that people don't really appreciate. Traditionally, they were used for thatching, for making roofs and so on, but they have many other really interesting functions. They provide a kind of soft engineering for storm surges and for wave action and so on, which means we don't have to build solid sea walls, so they take the energy out of the waves. They also filter water before it goes from agricultural land into the rivers and strip out all the nitrates and so on. So they have a purification function, they have a storm defence function, as well as providing lots of biodiversity for us as well.
And these sorts of functions, they're termed ecosystem services, and that's what your project is investigating and looking at. It's a rather ugly word, but I suppose it describes what it does.
Yes, I think the best way to think about them is that nature provides lots of benefits for us, and this is one of several habitats we're looking at in the United Kingdom. So we're looking at coastal marshes like these, we're looking at upland rivers, we're looking at lowland farms, and we're looking at urban areas as well down south in England. And we hope to extend that to many other kinds of habitats. And each of these habitats has lots of biodiversity which provides those kinds of benefits for us. Food production from agricultural land. In an area like this, there's lots of recreation provided for us as well as climate regulation in forests and so on. And what we're trying to do is find out how much of that biodiversity you really need to sustain those benefits in a changing world.
So are you trying to quantify this, to put numbers on this, to say, right, we need this many reeds to stop the flooding here, or we need this diversity of plants and insects?
That's right, and unless we quantify those, then they won't be valued properly in decision making. So many of these so-called benefits from the landscape, these ecosystem services, they don't actually have monetary value attached to them because we can't trade them. But actually, if we didn't have them, then we would have problems of flooding, they would have problems associated with climate change, carbon sequestration and so on. And we're trying to put numbers on those so that when we need to make decisions about the way we manage our landscapes in the UK, we can do that on a properly informed basis.
And so when we peer out through this slit across the water in front of us is almost like a pond. It's so still today. There's no wind at all. Then there's the reeds, and then there's a butterfly just flitting past. There's the pony in the distance, and then the river, and then into a sort of haze of the hill and trees. You put numbers and say, right, we need that, and that'll mean we get this amount of benefit from that.
That's right. So the kind of trade-offs that people like the Environment Agency, for instance, have to make on a daily basis, but we all do in society, is what should we do about whether we want to build sea defences to stop flooding or river defences to stop flooding? And one of the decisions we might want to make is not to invest huge amounts of money into those sea defences, but maybe to purchase adjacent agricultural land, which also has monetary value, in order to let that land accommodate the flood, rather than trying to stop it and then pushing the water further downstream. So that's why we're trying to put the numbers on these benefits, so that people can have a common currency, if you like. It doesn't have to be money, it can be anything, but a common currency to provide a rational basis for actually making those kinds of decisions.
Now I'm just watching that pony over there, swishing its tail, swishing the flies away, grazing on the marsh. I guess it's grazing on some grass or sedge or something over there. How do you put a number on the benefit of that grazing, or benefit or otherwise of that?
Well, that's what the project is really all about. What we want to know is, and that's a very good example for this conic pony, is how many conic ponies do you need to change the vegetation in such a way and keep it in a particular condition that it's the best possible condition to stop flooding? Because although it all looks like reed here, there's many, many species. And the central question is, how many species of these reeds and sedges do you actually need in order to provide that benefit of flood regulation or water purification for us? And, of course, the conic pony is one of the moderators of that biodiversity, because by feeding selectively, they can increase the diversity or decrease it. So that's a very good example of why biodiversity is important in these questions.
And you can hear more in the Planet Earth podcast, which is available via our website at nakedscientists.com/Planet Earth. It's the Naked Scientists, Chris Smith, Dave Ansell and Diana O'Carroll, speaking of whom they've gone off to the kitchen. Hello, you two.
Yes, hello. We are now in a very blue, very, very clean, actually, kitchen, which makes a surprise, makes a change. Also here, and not quite so clean, is Dave. Dave, what are we doing here?
Thank you very much, Diana. We're going to be making some waves. So obviously to make some waves, you need a fluid of some kind. And I've got the simplest fluid to get hold of. I've got a bottle with a third full of water here. It's a 2-litre lemonade bottle. And if we do the lid up and turn it on its side and you tip it slightly, you can get some nice waves travelling backwards and forwards quite quickly.
OK, so a 2-litre bottle filled a third full with water, tip it end to end, and it creates some waves. Why does it create these waves?
OK, so when you lift one end, that essentially lifts up the water there. Water wants to flow to the lowest place possible. That means it starts flowing and it bashes into the next bit of water, which pushes on that and lifts it up. And then that carries on going. And so you get this wave, this bump travelling along, which we call a wave. But that's kind of dull. You've all seen water waves. So first of all, I'm going to add a little bit of food colouring to make it a little bit more obvious.
Well, I'll tell you what, Dave. We've got a young person here called Ewan, who is our work experience student. Why don't we get him to help us make a mess? So Ewan's now holding some food colouring, and it's just being poured into the bottle.
Of drops in there.
Lovely. That's all spreading out in the water very nicely.
Give it a bit of a shake. Okay. And now, Ewan, if you top the rest of that bottle up very carefully, trying to pour it down the side of the bottle, all the way up with oil. So he's pouring vegetable oil on top of the water.
The vegetable is actually sitting on top of the water because obviously oil and water don't mix. What's special about oil that makes it float on the top?
It's essentially the molecules are slightly further apart. The atoms in them are slightly lighter than in water. There's less oxygen and more carbon. And so overall the density is about 0.6 that of water. So it's less dense than water, but not hugely so.
You haven't made any mess there, Ewan. Are you very experienced at filling bottles with oil?
No, not really.
No. So we're almost near the top now. It's looking very pretty. Lovely yellow on the top and blue on the bottom. Right, Dave's just screwing on the cap. There's almost no air in there at all. So what's happening next?
So if I turn it on its side again, and now if I lift one side like I did before, you still get waves, but they travel much more slowly.
Oh, wow. I'll try and explain what it looks like. It's quite spectacular, actually. What's happening is that the waves are moving almost in slow motion from one end of the bottle to the other. What is happening and why?
Well, in a wave, things are moving, and the force which is causing them to move is gravity. But strictly, the forces are not just to do with the gravity pulling down on the water at the bottom. Also, if you've got gravity pulling down on the oil above, those forces act in the opposite direction. So you're interested in the difference in force between the two. And if the two liquids have got very, very similar densities, then that difference is very, very small, which means all the forces are smaller, so the waves travel very, very slowly, so you get these slow waves. In fact, if the densities of the oil and the water were exactly the same, then there would be nothing to cause them to go back to a flat surface. So the waves would be incredibly slow, they wouldn't move at all, and it would just mix up at random.
So what are the real-world applications of this? Where are we going to see this kind of thing happening in the world?
Well, you can get these kind of gravity waves, a bit like water waves, in any place where you get a surface of a fluid. And if you have a surface of one fluid with another fluid over the top and they're a similar density, then they'll be very, very slow. So you find them in the atmosphere between very dense, cold air with warm, less dense air on the surface. And then you can get waves moving along on that boundary. And sometimes you can see them as clouds. This is because where the wave is going upwards, then the air expands a bit, cools, and you form a cloud. And where it goes downwards, then it contracts again and heats up. And you can also find them in the ocean, so you get very cold, heavy, salty water underneath, and you can get a surface with less dense water on the top. And you can get waves travelling along those, which can confuse nuclear submarines and their sonar. OK, so the important thing is just to have that difference in density. Back to you, Chris.
Thank you. And you can follow that up on the website, nakedscientist.com/kitchenscience, if you'd like to read all about it. Right now, though, Hannah Critchlow is obviously thinking about her pension in our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week we find out why men generally die before women.
My name's Steve. I'm enjoying the show from Philadelphia, Pennsylvania. We've all heard that women on average live longer than men. My question is, ignoring any outside influences like smoking, is there any fundamental difference between the longevity of the male versus the female body?
So, are there any biological reasons for why women outlive men? We first turn to Dr. Claudia Langenberg from Cambridge, who studies how lifestyle and genetics combine to affect your health.
The short answer is that the definitive reason is unknown. Men's death rate exceed women's at all ages, even early in life. And the more likely and complex answer is therefore that a combination of biological as well as behavioural and social differences contribute to the sex difference in life expectancy. One factor that is likely to play a major role is the advantage that women have from being protected from so-called male diseases, such as cardiovascular disease, which they are at lower risk of and are getting later in life, even considering their on average healthier lifestyle. Sex differences in longevity exist in almost all wild animal species. And because the lifespan of a species is correlated with the duration of time that the offspring depend on their parents, some have argued that evolution favours maternal longevity. This does, of course, not mean that keeping your children at home will make you live any longer.
So, women may be protected from male diseases in order to help raise the next generation. But what could be the biological mechanism behind this? We zoom into cells with Dr. Emma Barrett from the University of East Anglia.
The lifespan of our cells is at least partly determined by things called telomeres. Like the plastic bits at the end of a shoelace, telomeres cap our strands of genetic material and protect the ends from fraying. These telomeres get cut down in size each time a cell divides. When the telomeres become too short, the cell can no longer replicate properly. So instead of allowing the cell to misfunction and replicate in an out-of-control way, as is seen in cancer, the short telomeres signal for the cell to commit suicide. Although telomere lengths of babies are the same in both sexes, adult men's telomeres are on average shorter than women's. This sexual inequality in telomere loss appears to be because of the different hormones racing around male and female bodies. Estrogen is found in higher concentrations in women and seems to provide a degree of protection for telomeres. Estrogen reduces the effect that life stresses can have on shortening telomeres and may even promote telomere growth. So women's cells are better able to carry on replicating for longer than men because of their exposure to estrogen.
And this question has caused quite a fascination on Facebook, with Gerard McMullen arguing that a candle that burns brighter does not last as long, whilst Megan Radcliffe via Twitter retaliates, saying that women deserve some extra time for putting up with men. Now, moving over to next week's riddle, where we ask for your help in busting this biological criminal conundrum.
My name is Rick Santiago and I live in Rio de Janeiro, Brazil. Imagine that a criminal knows that he runs the risk of leaving some incriminating material like hair or blood in a crime scene. Would he be able, by means of genetic therapy, to change the inner layer of the mouth to prevent that any cells that he left on the crime scene will still match his inner cheek cells?
So, if police take a swab from the inside of our cheeks, could we alter our cheeks' DNA and stop ourselves being incriminated at a crime scene? Send your thoughts to Chris at thenakedscientist.com, tweet at nakedscientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. And talking of crime scenes and crime scene investigations, that's the subject of next week's show, where we'll also introduce a plastic that can detect explosives. That's it for this week. Thank you for joining us, and thank you very much to our guest Colin Black and to Diana O'Carroll and Dave Ansell and our production team, Mira Senthillingham, Hannah Critchlow, Tom Simpkins and Ben Valsler. Until next time, goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.